Okay, example problem number 3 for the water balance equation. This time we're going to be applying the water balance equation over an entire watershed or drainage area. And we're going to be looking at the James River in Virginia. And so let's start off with what we're given in our problem. So we're given the drainage area, which we'll call A, is 11,839 square kilometers. And so let's draw our picture. We don't really know what the watershed looks like, but we can draw a little schematic of our watershed. And we're given that the mean annual runoff out of the watershed, so what this is saying is we've got a stream gauge at the outlet of the watershed, and it's measured the stream flow in the James River over the course of the year, and the average of all the daily stream flows for the year gives us our average annual runoff. So we're going to call this Q, and so this is our mean annual runoff, and it's 144.4 cubic meters per second. Now we know that the river didn't flow at a constant rate over the year, but this average rate represents the same total volume of water as all the variability. So it would rain, the river would come up, go down, and we average it over the year, and this is that average rate. And the average annual rainfall, so we have precip on the watershed. So this is our average annual precip, P, is 1.08 meters. So quite a lot more rainfall than we get here in Grand Junction. Our average annual rainfall here in Grand Junction is only 9 inches per year, and they're getting 1.1 meters, so over 3 feet of rain per year there. All right, so what we want to find is our average annual evapotranspiration, which we're going to call ET. So that's the water that is evaporating from the soils, from any surface water, and transpiring from any plants. So that's all the water that's leaving this whole watershed, this 11,800 square kilometer watershed, that's moving from the land surface into the atmosphere. All right, and what we're going to assume is that there are no losses to groundwater, that any groundwater that soaks in becomes surface water flow and is actually captured in this measurement of stream flow. So we're saying that there's no loss of groundwater to adjacent watersheds, that all the water that soaks in the ground makes it into the stream and exits, which is a pretty reasonable assumption. The other thing that we're going to do, and we often do this when we're looking at whole watersheds over a year, is we're going to assume that the change in storage of water in the watershed is 0. Okay, so we're going to assume that delta S equals 0. Oh, and I forgot to mention up here our time period, delta T, is 1 year. So the reason we can make this is a pretty safe assumption, is that if our year goes, of course, for a year, so we start, say, October 1 to September 30th, the assumption is that the volume of water stored in the watershed is the same on October 1st as it is on September 30th. Now, it may change over the course of the year, but the net change in water we're assuming is 0, which is a pretty fair assumption as long as you haven't entered like a major drought period or had gone from a drought to a flood, where you had a lot less water and now you have a lot more, or vice versa. So, okay, so let's set up our equation. So we're going to do our water balance equation. And the usual in minus out is equal to the change in storage. In this case, our inflow is P, and our outflow is ET, and our stream flow, and that's going to be equal to 0. And we need to solve for ET. So what we end up with is that our ET is just equal to the precipitation minus the runoff. So that's the equation we're looking for. And we have precipitation in meters. We have runoff in cubic meters per second. We want ET in meters because we want it in units of depth over the year. And so we just need to convert. So we need to convert Q to meters per year. And so what we're going to have to do is we're going to have to divide by the watershed area, and we're going to have to convert seconds to a year. So draw a line there, and so let's start over here. So we're going to convert Q to meters per year. So Q is equal to 144.4 meters cubed per second. And we need to divide by our 11,839 square kilometers. So that's our area, right? So we're dividing by our area, but we have square kilometers here, cubic meters up here. So we need to convert, we're going to convert our square kilometers to square meters. There are 1,000 meters per kilometer, but we have to square that. So that means we have 1,000,000 square meters per square kilometers. So this will be times 10 to the 6 meters square per kilometer square. And then we have to, well, let me just do our little unit cancellation here, right? We have our square kilometers cancel out there, and these square meters are going to get rid of 2 of those. So now what we have on the top is meters per second. So now we need to get from seconds to a year, and there are 86,400 seconds per day and 365 days per year. So our days cancel, our seconds cancel, and we have meters per year, which is what we want. And this works out to be 0.38 meters per year. So now we have, here's our equation we're solving. I'm going to box that in a different color so we can see it better. This is what we want to do. We have P in meters, we have Q in meters now. So now let's solve for our ET is equal to 1.08 meters minus 0.38 meters. And that tells us that our ET is 0.7 meters. And this is our average annual evapotranspiration. So a little less than a meter, so it actually rains more than it evaporates, which is very different from what we have in Grand Junction, where we have a lot less rain, and because it's hot and dry, especially if you had open water, your evaporation will be higher. But it's a little bit less than lake evaporation of 1 meter per year measured at Richmond, Virginia. And it's very common that your actual ET from a hill slope or a whole watershed will be less than your open water lake evaporation. So that actually makes a lot of sense. All right.